Let's imagine a single particle. We'll call that particle number 1. And it's surrounded by a bunch of other particles. So imagine that we have an oxygen molecule and we've got all these nitrogen molecules around. We know in the gas phase this is going to be whizzing around and it's just going to go from collision to collision, just banging into one molecule, one molecule of nitrogen to another. Okay, so we want to know how many collisions per second. So we'll call this the collision rate for a single particle of 1, and it is going to be collisions per second. And so really it's going to have units of just 1 over second. Okay, so how do we calculate this? Well, if we think about this, it's going to be a function of a couple different parameters. First, the collision cross-section. So if we imagine that each of these particles are mathematical points, they can't bang into each other because there's nothing to bang into. But what if instead of being a mathematical point, they were really big? Obviously, it'd be easier for them to bang into each other. If we make them bigger and bigger, we see that the chances of them colliding are even bigger. So collision cross-section is basically a cross-sectional area where these two molecules are going to overlap. So it's going to have units of meters squared. So it's like imagining two trains colliding. The chance of them colliding, actually trains aren't a good example, they're on a track. It's like if you had two trucks colliding. You could have trucks with several trailers behind them. That doesn't increase the odds they'll collide. It's all about cross-sectional area. So the area of the front of the truck tells you whether it's going to collide with another one. So it's how wide it is. So it has units of meters squared. What also matters is the speed, specifically the relative speed. If we imagine that we have two molecules and they're both going fast, but they're both going the same direction, and they're going at exactly the same speed, they're never going to collide. So what matters is the speed of approach between the molecules. The faster that is, the more collisions we're going to have per second. So relative speed, of course, meters per second. And finally, it matters how many molecules there are. If we have this molecule and it's in a near vacuum, it doesn't have any collision partners. But if we put it into a really high pressure gases, we know there's going to be more collision. So this is the number density, just how many molecules per cubic meter. And remember, we're talking about collisions of 1 with these other molecules that we're calling molecule 2. So it's the number density specifically of molecule number 2. And number density is just number per meter, per volume, so per meter cubed. So if we multiply these together, we can see that meters squared and meters are going to cancel meters cubed down here, and we end up with units of 1 over second, and that's what we want. So all we have to do is come up with expressions for each of these terms, and we'll have an equation for the collision rate. All right, collision cross-section. So if we imagine a molecule of 2 and a molecule of 1, they're not necessarily heading straight towards each other. This might be going in this direction, this might be going in this direction, and we can continue those lines like this. If we imagine putting our eyeball right here and just looking at where they're going to collide, what we'd see is relative to our eyeball, we'd see one molecule coming in from the left, other one coming in from the right. So it looks something like this. We'd have 2, and we have 1. 2's coming in from the left, 1's coming in from the right. And we can continue these center-to-center lines along the plane of collision. And we can parameterize how close they are by a number b. And we can see that even though it looks like these are going to collide from above, when we have our eyeball here, we see they might not. What if b is big? In other words, what if this is not in the same plane? What if this is above the plane of the paper and this is in the plane of the paper? by quite a bit, they might actually miss each other, even though their paths seem to cross. And so we can see we can collide if B is less than the sum of the radii, right? If these are little dots and B is big, they're just going to cross like this without colliding. And this is true if the molecules don't attract each other. If they attract each other, their paths will be curved and they'll draw each other in. So what we're doing here in this simple collision theory is we're assuming that they're ideal gases, which means they're going to have straight paths until they collide. Okay, so collision cross-section is defined as the area which these are exposing to one another. Oops. Collision cross-section. And it's usually given the symbol sigma, and sigma is equal to pi times R1, oops, that's not squared yet, R1 plus R2 squared. And why does that make sense? Well, if we imagine looking at this, here's molecule 1. Imagine we draw a bunch of molecule 2s. And of course, they each have radius of a molecule 2. If we draw a circle here, we can say if any molecule 2 is inside that circle, when molecule 1 comes barreling through, it's going to get hit, right? On the other hand, if molecule 2 center is not within the circle, it won't get hit, right? If I had a molecule 2 over here, it's not going to get hit. So this area of this circle here, this circle, this sort of zone of destruction, is going to be radius 1 plus radius 2, and so its area, of course, is pi r squared. So the combined radius squared times pi. Okay. In practice, scientists use an experimental parameter that closely matches this. So this is a theoretical collision cross-section. You can also get experimental values of sigma from beam scattering experiments. This is close enough, though. Just use the van der Waals radius of each atom or molecule if it's a molecule. Add them up, pi r squared. Now we've got our estimate of collision cross-sectional area. So notice we've got meters squared. Typical values for collision cross-section are going to be on the order of 10 to the 19th meters squared. And you can see why. If you plug in a typical radius for a molecule, it might be a few hundred picometers. So you get that plus that, so maybe several hundred picometers. Square that times pi, you'll end up with a number that's on that order. Now, we already said the relative speed that matters, right? We have a bunch of ice skaters, and they're all going with the flow. They're all skating the same way on the rink. Or roller skaters, we don't have a lot of collisions. On the other hand, let's imagine we have a bunch of 12-year-old children. They tend to skate in this disorganized manner. We know what's going to happen. There's going to be lots of collisions. So it is relative speed that determines the number of collisions. So it turns out relative speed is actually really easy to calculate. We know that the VRMS was going to be 3 RT over m. And the average speed is going to be 8 RT, that's a Mohr mass here, pi times the Mohr mass, take the square root of that. And of course we could just as well have written this in terms of, these are the molar thermal energies and the molar mass. We could just as well have written this in terms of single molecule thermal energies and of course single molecule masses. So either one is fine, just don't mix and match, right? And if you write your units, you'll have per mole here and here you won't, and so you'll realize you'll be able to keep it consistent. But what about the relative speed? Well, the relative speed is very similar to the average speed, except for instead of using the mass, we used the reduced mass. And once again, you could do that using molar or single particle formulation. So what in the world is a reduced mass? The reduced mass is basically the mass of one particle relative to another. So we say mu is defined this way. We've got the mass of one particle and the mass of another particle divided by their sum. And reduced mass is an extremely useful concept. You use this in physics and in quantum mechanics whenever you have two bodies that are moving relative to one another. So the sun and the earth, or the earth and the moon, or an electron and a nucleus. And what this allows you to do is to reduce a two-bodied problem to a one-body problem. And notice one characteristic of the reduced mass is that, let's imagine that M1 is much, much greater than M2. Well, in that case, we can see the reduced mass. What's going to happen? Well, 2 is negligible, so we can leave it off, which means we can cross out these two. It's going to be equal to M2. So that tells you if you have something really, really heavy, like the sun, and something really, really light, well, relatively speaking, like the Earth, the reduced mass is going to be the mass of this lighter thing, which means we can just treat it as if the Earth is moving and the sun is stationary, even though we know in truth they're actually moving around their common center of mass. Well, one other aspect of reduced mass is that if we make a different supposition, if M1 and M2 are the same, we can see that this is going to be 2m and this is going to be m squared, and that reduces just to m1 over 2. And whenever we count up individual particles, we use the asterisk to say we're not talking about moles, we're talking about just numbers here. So this is going to be equal to the number of particles divided by the volume. And so it's just molecules per meter cubed. So it's units of reciprocal meters cubed. And we can just use ideal gas behavior. So we already assumed the particles aren't attracting each other anyway. So we already assumed the ideal gas law when we did our collision cross-section calculation. So if we assume that, we know that PV is equal to nRT, or we can say PV is equal to nKT, and we just divide V by, or we divide N by V rather. So we have N divided by V is going to give us P over KT. Great. So now we have all the pieces we need to calculate our collision cross-section. Great. So now we have all the pieces we need to calculate our collision rate. So we said Z is equal to the collision cross-section times the reduced speed, or the relative speed, times the number density. So we have a collision cross-section. We know this is going to be the square root of 8 kT over pi times the reduced mass. And we're going to multiply that by the number density, and we said that's proportional to the pressure. And if we want to, we can simplify this a little bit by taking this kT, squaring it, putting it inside here, which it comes out as being squared. So we have 8 kT pi mu, and then when we put these inside, they have to square. And so we can cancel. And we get our final equation for, this is supposed to be at times, we get the final equation for our single particle collision rate, where we have 8 over pi mu kT times the pressure. And notice the higher the pressure, and what is this the pressure of? This is the pressure of particle 2. Remember, because we were trying to find the number density of the collision partner, which was particle 2. Okay? So this is the partial pressure of particle 2. And this is the collision rate of particle 1 with all the particle 2s. So remember, we've got 1, and then we've got a bunch of particle 2s, etc. Okay? So this is the collision rate, how many collisions per second molecule 1 has with any one of these molecule 2s. Okay, so make sure you understand that this is the mass of the reduced mass of the particle 1-2 system, but this is the partial pressure of particle 2. Okay? Great.